All right, we are going to talk about calculating the cell potential of galvanic cells. So remember again, these are electrochemical cells that are spontaneous, and we're going to see how they provide voltages that are greater than zero. And they can be used to power a fan or a light bulb, or maybe even charge your cell phone, for example. All right, so let's talk about potentials. A potential, or an electrochemical potential, is simply a measure of the chemical potential in units of voltage, all right? And another way to think about this is that it's a driving force for a charge transfer process. And of course, we're talking about a redox reaction, okay? So if you look at this chemical reaction here, we have silver ion, okay, which is aqueous, reacting with an electron to produce solid silver. And the reduction potential here is equal to 0.7996 volts. Now, this is a spontaneous process, and you can think of it as being a ball on a hill, for example, and it's going to roll downhill and potentially release this amount of energy, electricity, let's call it, okay? Lithium ion can react with an electron to provide lithium metal. And the reduction potential here is negative 3.04 volts. This is a negative value, and this is not spontaneous. So if you want this reaction to go, the electrons need to come from an outlet, okay? So this is what happens when you charge your cell phone. You plug this into a wall, and the electrons from the power grid there are going to go into lithium ions in your lithium battery and transform that to lithium metal. So that's going to be like you putting a ball on the ground and then lifting it up, okay? So you're going to provide some amount of energy to increase that potential, okay? So in summary here, if E is greater than 0, the reaction is spontaneous. It happens all by itself. It's going to be like a AA battery, okay? You can hook that up to a light bulb, in a flashlight, turn it on, and it's going to work by itself. When E is less than 0, that is not spontaneous, and that's like charging a rechargeable battery, like your nickel metal hydride batteries or your cell phone, for example, okay? Now, Appendix L in the OpenStax chemistry textbooks gives you all of the reduction potentials. I'll also provide a little chart in my CAMUS module as well, but this is where you want to go to find the electrochemical potentials. Now, this is only for reduction, and if you look at all of these reactions here, you can see the electrons are on the left, and this is very extensive. It goes on for quite a few pages, okay? I'll provide a link in the description of this video for your reference. Now, when we're talking about cell potentials, the cell potential, not the reduction potential, but the cell potential is for the overall redox reaction. Now remember, you have your anode and your cathode, the two half reactions, and the cell potential is going to be equal to the reduction potential minus the oxidation potential, okay? So E cell is the cell potential for the galvanic cell, and again, this is an electrochemical cell or a voltaic cell, right? E red there is the standard reduction potential, and that occurs at the cathode. We'll see this a couple times with some examples and on the summary at the end of the slide. You'll need to memorize this, okay? Reduction is gain of electrons. That happens at the cathode. The oxidation potential, or the standard oxidation potential, occurs at the anode, okay? So how do we use all this information and keep track of it all? Let's do an example. So what is the E cell? That stands for standard cell potential for the galvanic cell pictured. I showed this cell potential, this galvanic cell in my other video previously. On the left, you can see copper, that brown colored thing, and copper ion, which is the bluish solution. And on the right, we have silver, which is that bar there, and we have silver ion in solution, okay? So the first thing you want to do is think about what is happening at the cathode. It's actually labeled here. The cathode is the beaker on the right. Ag plus 1 electron goes to silver solid. Now remember, that's where reduction occurs. Reduction is gain of electrons. Okay? you go to the table here and you try to find something that matches. And I see Ag plus electron, arrow Ag. So the voltage there is 0.7996 V. Now, if you see V, that doesn't mean volume. You're not plugging in liters or something like that. V just stands for volts or voltage, all right? Next, we think about the anode. Here it's labeled in the beaker or the diagram. We have copper solid going to produce copper ion plus 2 electrons. Remember that the anode is where oxidation occurs, and oxidation is loss of electrons. We have that phrase oil rig. Oxidation is loss of electrons. Oil rig, the rig part, reduction is gain of electrons, right? So anode, oxidation, losing electrons. This is the half reaction that's happening, all right? We go look at our tables and it doesn't look like anything matches up. Everything's kind of flipped here. We have electrons on the left, but for our anode reaction, we have electrons on the right. And this is to be expected. Your anode is always going to be flipped in the table, and this is why we have a minus sign in the equation. So the one that matches here is the copper 2 ion, okay? I've circled it. And that value here, I've also circled it, is positive 0.34 volts, all right? Once you've grabbed your 2 voltages off of the table, you want to now use the formula. The cell is equal to the reduction potential minus the oxidation potential. And here it's simple math, 0.7996 minus 0.34 volts. And I'm using the rules of significant figures to round my final answer to 2 decimal places. I have 0.46. Capital V, which stands for volts. Now here's where I want to mention that if E is greater than 0, or if it's a positive voltage, right, for the cell potential, the reaction is going to be spontaneous. So this will happen all by itself, meaning it will produce electricity. You could use that to power a fan, for example, on this very hot, humid day. Another example, here is number 21 from the OpenStax Chemistry 2nd edition chemistry textbook. All right. Calculate the standard cell potential for this reaction, and we have a balanced chemical reaction, and we want to say whether the reaction is spontaneous under standard state conditions. So first, you want to figure out what is being reduced, okay? Reduction is gain of electrons. What is gaining electrons? Magnesium going to magnesium ion is losing electrons. So we have nickel 2 ion going to nickel. That's gaining 2 electrons. So you kind of have to figure it out here. That, therefore, is going to happen at the cathode. And we want to look in our tables, look around for nickel. There it is. I found it. There's only one in the table, and it's negative 0.257 volts. And you want to write that down. This is the reduction potential, okay? Reduction is gain of electrons. Next, you want to figure out what is being oxidized. Magnesium is neutral. It's a solid. It's an element. It's an atom, right? It's neutral in the periodic table. And when it transforms to magnesium ion, it has a +2 charge. It's losing 2 electrons. So that's called oxidation, because oxidation is loss of electrons. So you hunt around for that reaction. There's a mistake here in the OpenStax Chemistry textbook. I just cannot control it, but that should be magnesium 2 plus. As the ion, +2 electrons going to magnesium. Once again, it looks flipped, but that's the closest match there. And the E for this is negative 2.372 volts. Why is it such a large value? Well, magnesium is rather electropositive. It's located on the very left of the periodic table. It's desperate to lose those 2 electrons to get an octet structure. We've learned about that in Chemistry 111, but anyways, that's why it's such a big number. It's a very reactive metal, okay? So it's even harder to get magnesium 2 ion to go to magnesium, all right? Anyway, that as an aside, now that we have these 2 individual voltages for the half reactions, we can use our wonderful formula here. The reduction potential minus the oxidation potential is going to give you the cell potential. And here I just wanted to emphasize that you're subtracting a negative 2.372 volts. So this is why you have a positive 2.115 volts at the end. All right? And the question asks you to say whether it's spontaneous or not. And since the final number we get is a positive number, we can say that it's spontaneous. This is going to happen. Okay? Once again, the driving force here is magnesium is going to form an octet structure, so that's why it kind of disturbs nickel and forces those 2 electrons on nickel. All right, here's the summary here. You need to memorize that the cathode is where reduction occurs, and that's going to be the reduction potential table, okay? So that's E red from the table. And then the anode is where oxidation occurs. That's losing electrons, okay? And that's E ox. We don't have a table of that, but you're going to find that in the reduction table flipped, okay? Flipped, that's the one that's flipped. And you're going to use this formula. You just subtract the 2 numbers, and you get your final cell potential. And that's going to happen only at standard state, 25 degrees Celsius, 1 atmosphere for the gases, and 1 molar for the ions. And that's it for the electrochemistry introduction here. Thanks for watching. Please consider subscribing to support my channel, and have a wonderful afternoon.